Okay, hello everyone. My name is Noam Moshe, and I'm here to present to you this presentation. Who is your parser and what does it do? URL parsing gone wrong. So let's start a little bit about myself, a little bit of who am I. I'm a vulnerability researcher at Clarity Research. Clarity is a OT SCADA-based company that offers security solutions. And as a definition of that, I mainly research IoT and OT environments. However, I do get to play a little bit with run-of-the-mill popular applications, and of course, in my free time. I am also a CTF player, and I enjoy playing CTFs, and I think it's a great environment to learn and expand your skills. So this is a little bit about what we're going to talk about in the next half an hour. We're going to do a bit of introduction about URL parsing, what is a URL, how can you parse it, and then we're going to showcase how different URL parsers actually produce different results and how different parsers might get confused and think a URL is one thing instead of another. We're going to show some vulnerable code snippets that's going to showcase those confusion. And lastly, we're going to show a case study about real-life vulnerabilities we've managed to identify, showcasing the finding of our research. So let's do a quick rundown about what is a URL. So we might all know it, but just let's do it quickly. A URL is actually created from a few URL components. They are being scheme, authority, path, query, and fragment. Let's start with the first part, which is the scheme. Well, the scheme dictates what protocol should be used to parse the URL, be it HTTP, HTTPS, FTP, etc. And you can actually, there are a wide range of schemes and protocols that are all defined in a separate RFC, showcasing how to parse the URL of this specific scheme. Then we have the authority. Authority is actually created from three things: a user info, host, and port. And this is just basically the server that holds the data we are looking for. The only mandatory part is the host, and user info and port could be specified. There, for all protocols, there are actually a default port, so it is not necessary. Sometimes authority is called netlock by some URL parsers. Then we have the path. The path is actually the path that points to the resource being requested. Lastly, or before lastly, we have the query, which gives users the abilities to supply some parameters to the server. And then lastly, we have the fragment, which is used to identify an inner resource inside our resource. For example, if you're reading an essay and you want to jump straight to a specific paragraph, you can specify section 3 or paragraph 2, whatever, and that way the server knows how to direct you. So it all seems quite easy and quite easy to understand. So what's so hard? And the problem arises when we understand that there are actually many different parsers, be it different programming languages like Python, Ruby, Java, CPP, and PHP, or even different tools. I mean, a browser, for example, parses URLs all the time. Whenever you click on it, whenever you type it, whenever the server returns the URL, it is being parsed all the time. Same goes for tools like curl and wget. So there are many different parsers, and not all of them produce the same results. Furthermore, URLs will actually change quite a lot. There are many RFCs defining the URLs, and they will change over the years. Now, when you think about parsers that were written long ago or still want to be backward compatible, some parsers might actually choose to not be latest RFC compliant and instead be compliant to older RFC. The most dominant example of which is Python's built-in URL lib, which is a URL parsing lib, which is not conformant to RFC 3986, instead being conformant to an older RFC, RFC 1808. So in this paper, we've chosen to talk about a few things in particular and focus on a few things. We don't showcase the entire research we've done. We have an add-on of a research paper that showcases the entire research we've done. In this paper, in this presentation, we're going to talk about URL lib in particular, curl and browsers, because they are the most predominant URL parsers in the market right now, and of course request and URL lib 3. If we're already talking about Python, those two are another very predominant parsers. Okay, so let's do a little bit of an example. and an act. Let's start by parsing this URL. Well, as it turns out, it's actually pretty easy, https://google.com. Well, here's the result, and this result is being returned from Python URL split. And as we can see and guess and clearly see with our eyes, the scheme is HTTPS, the netlock or authority is google.com, and there is no path query or fragment. That was pretty easy, but now let's look at a little bit of more complicated cases. For example, take a look at this URL. Take a look at this URL, google.com. Well, this might be the most common URL we are regularly typing. We usually don't type the scheme, we don't type it, we don't have time for it, we don't use it. However, for parser, it is actually quite important. They are using the scheme to know how to parse the URL and when to start parsing it at. So when we parse google.com, well, as it turns out, the URL split get confused. And while the scheme is empty, it does also think the authority or netlock is empty as well. Instead, he thinks google.com is the path, meaning this is a relative URL with no host name. Well, as it turns out, not all parsers think so. For example, urllib3 and curl, well, they accept google.com as a valid URL. And whenever you fetch google.com, they just append the default scheme of HTTPS or HTTP and just fulfill the request as if it was very, very simple and containing it. So that was a very easy confusion. Let's look into a little bit of more complicated confusion. Let's look at this URL, HTTPS column, and then we've added multiple slashes to google.com. Well, when we give URL split this URL to parse, we find out that once again it was confused. Once again, scheme is HTTPS, which, yeah, that is the scheme. However, netlock, the authority, is empty once again. Why is that? The reason the netlock is empty is because of how URL split parses the URL. What URL split does is behind the scene, it looks for the column / after the scheme, and then it just think, okay, here starts the host name. Let's go until we find the next delimiter. And what is the delimiter? Well, it depends on what the next URL component is. If it's a fragment, the next delimiter is a hashtag. If it's a query, it's a question mark. And if it's a path, the next delimiter is a slash. Because we have 3 slashes right one after another, the parser thinks netlock is empty because there's nothing in between the first 2 slashes and the third. Instead, it thinks the path is // google.com. Very interesting. However, when we look into how Chrome and most modern browsers parse this URL, we find out that they just ignore the extra slashes. They don't care about the extra slashes and they treat it as if it was the same as HTTPS column / www.google.com. And they fulfill the promise and the fetch as if it was regular. And when we look into curl, we find something even more interesting. Curl somewhat disregards extra slashes. When curl is given 4 or more slashes, it says, whoa, the URL is malformed, I cannot accept it. But when it is given 3 or 1 slashes, it says, okay, that's, a little bit malformed, but I'm still going to accept it. I guess curl only allows you to make 1 mistake. Let's look at this URL, and as you can already guess, // google.com, once again, scheme is empty, no netlock, because immediately after the first 2 slashes, there is a third one, and the path is google.com. But now let's look into how Chrome treats this URL, and we find out that once again, Chrome doesn't care about the scheme. It will treat this URL as if it was the same scheme as the default one, HTTP or HTTPS. And if you are in an HTTP server, you will still keep the HTTPS session. Okay, that was very cool. Let's look into another confusion, and the last confusion I'm going to present. And this is URL encoded confusion. Some say there is no place like home, except here it's not home, it's 127.0.0.1, or actually it's 127.0.0.1 URL encoded. And let's try and parse this URL. So when we give it to URL split, it does not URL decode it. So the scheme is HTTPS, as we can see, and the netlock is not 127.0.0.1. Instead, it's the URL encoded data. But now let's try and fetch it. And when we fetch it using request or URLlib, we actually find out that it does URL decode it, and it does fetch it to 127.0.0.1. And well, I guess it doesn't think it's its job to decode it, but only sometimes. I'm not really sure, but I guess it says it's not its job. Okay, so we've seen different parsers, and we've found out that some of them actually produce very different results. And I mean, that's very curious. So what can you do with it? What can you do with this discrepancy between different parsers? And well, it depends. If you are, you need to understand that there are actually different parsers for different needs. What it means is that, for example, when you are writing code and you are using a URL parser, it should be very strict. You should make sure there is no mistake in the URL, and it should all follow URL RFC and should be compatible with it. However, a browser is way more lenient, and the reason of that is that, well, we make mistakes. Whether I am a developer that just puts an extra slash or use backslash instead of a front slash, or even uses way more slashes or forget the scheme, the browser should always work. The browser knows that we make mistake, and it should work in more cases, and that's why it is complementing our mistakes and just ignores them and thinks, yeah, it's probably a mistake, let's just still treat the URL as if it was valid. And I guess that's a valid reason why one parser behaves so much differently from another, because they are for different uses. And when we look into Chromium's code base, we are seeing comments that, well, straight out says that what we've said is correct. They are straight out saying that they accept the scheme without the slashes, or they accept URLs without scheme, or they accept multiple or missing slashes, and they even accept backslashes instead of a slash. And when we look into bugs that were reported to them, they just straight out say, hey, we are choosing actively to not follow URL specification. And well, that just makes sense. So what can you do with this information? Well, it depends who you are. If you are a web developer, you should know and analyze and understand every parser that is being involved in your application, be it a backend application or a tool like Carol, wget, or even a browser if you are supplying front-end code. And if you are an attacker, you should know, hey, how can I trick these parsers? And how can I make sure and trick them into not performing correctly, not validating me? And this is what you should think about. And here is a very good table showcasing all of those confusions we've seen before. And as you can see, we've only chosen a partial list, mainly Python or curl and Chrome. But for full list, once again, check out the research blog. So what can we do with it? Well, as it turns out, most of those errors or vulnerabilities occur because of a talk to error. And talk to is a very simple concept. Basically, it means that there are two interactions with the URL. One for checking it, checking whether it's valid or not, and one for using it, be it fetching it or returning it, many different things. And because we have different parsers involved, if one parsers identify and parse this URL one thing and the other treats it very differently, it could lead to some serious mistake. Example of which can be an SSRF attack where you want to block certain URLs from being fetched. But if you can trick the browser, if you can trick the server into thinking this URL is not really what it leads to, you can actually bypass those mistakes. Another vulnerability that is plausible through these confusions is an open redirect attack, where you trick the server into redirecting unsuspecting users into a third-party site. Lastly, basically any validation check about URLs, you can bypass if you know the parser. And if the parser that is being used does not treat the URL the same as the parser that checks it. So let's showcase a few case studies, a few real-life vulnerabilities that we've identified, showcasing these confusions. And the first one is a null pointer dereference in Belladonna Linphone. And basically what it is a VoIP application. If you ever used a voice call, if you ever done video calling or messaging, anything over VoIP instead of cellular data, then you've probably used SIP behind the scene, because SIP is the predominant protocol for managing VoIP sessions. And when we look into how SIP is built and how SIP is used, this is a SIP message. And we can actually see that it is very familiar and very similar. And it reminds us a lot of HTTP or most other protocol that are header-based and textual-based. And just like HTTP, this request has, this invite SIP request has headers, which are specified by the header name, a column as a delimiter, and then the header value. And when we look into one thing in particular, we can see that is actually very similar to what we're talking about, and this is a SIP URL. As it turns out, SIP is a scheme. SIP is a protocol defining URLs. And it is very similar to regular URL being built from a scheme, a username, domain name, and port. So when we understand that the SIP is a URL, that SIP has SIP URLs, we understand that the servers must somehow parse it. And when we wanted to look at that, we've reached this code. This code is BetaSIP, a SIP parser that is used by many libraries. And this is how it parses the from header. And we can see that it is doing a very similar check. It takes the header and separates it to three parts. The from name, the header name, which in this case is from over F, the column, which is the separator, and then the header value, which is a from spec. And when we look into the from spec definition, we are encountering a very wide tree that has many different branches to different parsing primitives. And at the end of this tree, one specific tree branch leads us to this definition, path segments. And yeah, that reminds us a lot of your path. And that is because it is essentially the same thing. It is a path segment being separated by a slash as a delimiter. And because SIP parses a SIP URL and leads us to a path segment, it turns out the single slash or a path is a valid SIP URL according to BetaSIP SIP parser. And that's very interesting because if you remember this code that we've glimpsed over before, let's talk about what it does here. It tries to parse the SIP URL as a generic URI, which we know a derivative of is a path, and then it extracts the scheme and compares it to SIP or SIPS using strcompare. And the reason it does this is to check whether the URL is a SIP URL. But what happens when we give it a slash? A slash has no scheme. And here starts a very interesting interaction because the server will parse slash as a generic URI, but when it tries to extract the scheme, it will return null because there is no scheme. And then it will compare it, comparing null to SIP, doing a null pointer dereference, and then bam, we've reached a crash, all using this very simple payload of a single slash. That's very cool. And when we look into how it could be used, well, this is how it could be used. You can basically crash any application that uses BetaSIP remotely without any user interaction by sending them a single SIP package, an invite message using the malformed SIP URL. And that's very cool. Let's look into another vulnerability we've identified through looking into how URL is being parsed. And this vulnerability or vulnerabilities is an open redirect vulnerability. An open redirect vulnerability occurs when an attacker tricks a server into redirecting users to a malicious third-party site. And when they reach this site, they are under the attacker's control, and it could do a phishing campaign on them and try to extract credentials or credit cards, whatever. And that's actually very scary to websites, and that's why many websites try and not redirect users that are not actively clicking on a link to a third site. But why would website even redirect users? And that's a very basic question, and it's interesting. And as it turns out, servers use redirection quite a lot. Think about this case. You are surfing a forum and you click on a post, and then you need to be logged in and you are not. What happens? The server redirects you to the login page. What's next? After you've logged in, you don't want to go back to the home page. Instead, you want to go straight to the post you've been looking to reaching. Then the server needs to redirect you once again. And many servers want to do it, but when they want to do it, they still understand that simply redirecting users to a third-party site is dangerous. So they parse the URL and check whether it is malicious or not, whether they should redirect to it or not. And let's look into how they do it. The first vulnerable design pattern we've noticed is the relative versus absolute URLs. And let's talk about what it is. Basically, the server checks about the redirection URL and checks, hey, is it a relative URL or an absolute URL? So let's define what's an absolute URL and what's a relative URL. An absolute URL is a URL containing a scheme and a host name, pointing to a full URL. However, a relative URL does not have a scheme, does not have a host name, instead only having a path. What the server does or what the browser does is seeing that the URL is relative and instead just appending the current host name and scheme, thus still staying in the same domain. So if a server wants to redirect to a relative URL, that's safe because it's still in the same domain. But an absolute URL, it needs to check whether the domain is the same. So how can it do it? Well, that's actually pretty easy. It would parse the URL, and this is a vulnerable code snippet that we've identified. And it will parse the URL and then check, hey, does it have a scheme? Does it have a host? If so, that's an absolute URL and we need to check it. If not, it's relative and that's all good. So how can we trick this parser into thinking the URL is relative, meaning there is no scheme and host? Well, as it turns out, I've already shown you this cool trick. And this trick is the 3 slashes. Whenever the parser URL split parses // it thinks, yeah, there is no scheme, obviously. However, there is no netlock because 2 slashes are following immediately by the third one. So there is an empty netlock, there is an empty scheme, meaning there is no host. It's the same domain, it's a relative URL, let's pass it. However, whenever the browser will see the // it will treat it as a full URL missing a scheme and will redirect to evil.com. Here is the flow. I think it is very simple. And here is a POC redirecting to google.com. And because we are using a // it succeeds. We've noticed this vulnerable design pattern, and we've actually found it in many different parsers. And we took this one vulnerability and we found it in different applications. And we've managed to find 4 different CVEs, 4 different platforms that use this exact or very similar code pattern. So whenever you find something vulnerable or vulnerable code pattern, look wider, look for other applications that may be vulnerable. Okay, the second parsing primitive or vulnerable code snippet that we found is the forced relative. Let's say I need to redirect. How can I make sure the URL is safe? That's easy. Let's just force it to be relative. How do we force it to be relative? Like this. We parse the URL, we just negate, we drop the scheme and netlock, and then we unparse it and recreate the URL. But notice how no validation is performed. Notice how the server never checks the URL created. how can we abuse this? And as it turns out, that's pretty easy too. All you need to do is create a full URL, an absolute URL after the scheme and hostname, scheme and an authority are being removed. And here is our input, http column//evil.com. Whenever URL split parses it, it thinks, yeah, the scheme is HTTP. There is no netlock because there is no scheme : //. And then what is the location, the path, http column//evil.com. It will remove nothing, the HTTP and nothing. And then output is http column//evil.com. And we've managed to create another open redirect vulnerability. Once again, we've seen this code snippet and we found 2 more applications that use it, and we've managed to find 2 vulnerable platforms. Lastly, the starts with code snippet. Okay, let's say we have an absolute URL. Is it safe? That's easy. Let's check if it starts with our current domain. How can it be done? With something like this. What we're doing here is we're parsing the URL, we're checking if it has an authority, and if so, we check if it starts with our authority and scheme. Well, what's the problem here? Let's remember how authority is built, and then we can easily identify another vulnerability. An authority is built by user info, host, and ports. How can we abuse this? Easy. Let's just use the user info. And here is our malicious payload starting with the real site domain, however, pointing to evil.com. Once again, identify the vulnerable code snippet, find 2 vulnerabilities, easy vulnerabilities. Okay, so let's summarize. We've shown you how different URL parsers parse URLs, and I think there are actually unexpected and very wild parsing primitives and results. So make sure you are familiar with what parsers you are using. If you are developing an app, if you're checking an app, know what parsers are being used. And then after you know what parsers, know how the parsers are parsing. That it will always lead to some great findings. Lastly, guys, a little bit of credit and thanks. I'm gonna give a huge credit to Snyk research team for co-researching with us, and specifically to Kirill and Raul, who helped us both in doing this research and finding some vulnerabilities, and they were great help and really just a pleasure to work with. And lastly, thanks to Sharon, my team lead, for allowing me to do this very cool research. So thank you a lot, guys. Thanks for listening, and it was a pleasure. Thanks.